Good morning. Good morning. Welcome to the next higher level programming lecture. So I have two main topics today. First, we will talk about how you can structure your Python programs better through modules, how you can document your code. So I've touched on this. I just want to repeat it again because it's very important. And I want to talk about testing, which is very, very important nowadays when it comes to professional, but also academic software development. In the next part of the lecture, and that will continue also into the next lecture, will be all about making Python fast. So remember that in the first lecture I mentioned that these scripting programming languages, they're often quite slow. But I want to show you how we essentially can get the speed of C or C++ in a Python environment as well. So that's all about what we do this week and next week. But let's start with modules, documentation, and testing. So a Python module is essentially just a file that consists variables, functions, and classes. And you can imagine a module essentially being like a library. Right? So imagine you write your script, and it turns out that you have some useful functions that you want to maybe access from multiple of your scripts. What you can do is you can create a module, move all these functions into that module, and then access these functions from the different scripts. So in essence, a module helps you to avoid writing out functions that you've already written. So when do you want to use modules? Well, essentially, it helps you to organize your code. You can split your script into multiple functions and into multiple files for easier maintenance. You can group related code into one module, one file. So maybe you want to have one module where you collect all the mathematical functions that are relevant to your script. Or anything that is related to input and output could be one module. Then you can use it to share common code between scripts. And of course, you can, once you've collected all these useful functions, you can publish them on the web and give them to other people. And so you've been using modules essentially from the very start. And the way you use them is with this import statement. So by writing import sys, we actually import the sys module in Python, which is a module that is installed by default. So we always have it accessible. And then we can use it by stating the module name, in this case sys, dot, and then whatever variable or function or class that module contains. Right? So in particular here, the sys module contains a variable called .argv, and it turns out that this variable is a list, so we access the second component. So that's how you use modules. You can also, rather than importing the entire module, you can also import just one variable or one function or one class of that module. And the way you write this is you type in from sys import argv, where sys is the module name and argv is the variable name or the function name. And then you can import all the, so here note the difference. There's a syntax difference between the first and the second example. In the first example, I had to, when I wanted to use the module variable, I had to write sys.argv. While in the second example here, I didn't need to state the sys anymore. I could just use argv. So in essence, in the second example, you import the variable directly. You don't have to state the module name anymore. And if you want to import all the variables in the module, you can write from sys import star, and then in this case, you get argv and all the other stuff that is contained in the module. So typically, the last one is not recommended because you might import variables that you're not aware of. So for instance, here, I import all the flags, and then I say flags equals the empty string, but it turns out that instead of creating a new variable here with the empty string, I actually overwrite what has been. So the flex variable is also contained in the sys module. So actually, I'm changing in the sys module variable. So that's the side effects of importing everything. But maybe the more interesting part is how to make your own module, because that we haven't seen yet. And actually, making module is extremely simple in Python. All you need to do is you create a new .py file, for instance, mymodule.py, and you put all your functions and variables and classes in there. And that's it. Then you have a module. So in order to use that, you have to put this file in a directory where Python can find it. And I'll show you in a second which directories are suitable for that. So then, once we've created this file, and you've put it in a nice directory, then you can start using it. So then you can write import mymodule and import mymodule SMM if you want to give it a different name. Or from mymodule import star to import all the functions. Or mymodule import myfunction, assuming that you've put a function called myfunction into your module. And so you just use it as any other module that we've seen so far. So then comes the question, how does Python find your modules? And essentially, Python has different strategies for looking for modules. So it will look into kind of a standard installation directory where all the default modules and packages are installed. And so that depends on your operating system and your Python version. So in my case, it's user lib Python 3.5 side packages. So if you're in a Ubuntu system, you could kind of look in this directory and you will see that there's loads of modules in that, or packages in this case. The other directory where it's going to look at is all the paths that are defined by the environment variable Python path. I'll show you in a second how you can change that. And very useful, it will also look in your current directory. So if you put your module just in the directory where you're working in anyway, then it will automatically work. So then how does this Python path work? So essentially, in Bash, we talked about environment variables. And this Python path is one that Python always looks for. So I can output my content of the Python path variable by using echo. And so I get a colon-separated list of directories. So I get one directory here and a second directory here. And Python will look in these directories for modules. So essentially, if you now have a new directory where you have loads of modules that you want to use, you just need to extend that directory into that variable. So how do we do that? Let's say I have this new path, home cmon mymod, where I store my modules. And so then I use this line here, export Python path equals the new path, colon, and then I just append the previous Python path variable. So I just add one more path to Python path. Okay, and then I can just echo it out again to make sure that to ensure that indeed all my three paths are stated. And so now it will automatically, if you write import x from mymod, it will automatically work. So one thing that's really useful is often, let's say you created a module and you have 10 different functions implemented. And sometimes it's useful to also be able to just write Python and then module name, and then it should just maybe run some tests on these functions, or maybe just some use cases on these functions to demonstrate how to use the functions in the module. And so the way you can do that is by using this if statement here at the very end of your, I put it at the end of my module file. So if you write if name equals, sorry, there are two underscores here that are not visible on the slides. It's underscore underscore name underscore underscore equals underscore underscore main underscore underscore. And then you have some code here that makes use of the functions in the module. So then the trick is that if you write Python, if you in your bash, if you execute that module name, that module file, so if you write Python module name.py, then it will go into that if statement and actually execute these lines. But if you write from another file, if you write import module.py, then it will not run this code. Right? So essentially, what I often do is I define all my functions in the module, and then at the end I have an if statement here, and then inside the if code I have some example, just some examples on how the functions in the module can be used. And I use that also to just test that everything still works in the module. So then the next layer above modules are packages. So in file systems, it's the same. We have files, and then we have directories. And so in Python, it's just called module is a Python file, and then a directory is a package. So of course, a package contains a set of modules, or a set of modules can be collected in a package. So put everything in many modules in one directory. And then in order to make a directory a package, the way it's defined in Python that you need to have this _init__.py file. That's the definition of a Python package. So as soon as you put this file in a directory, it becomes a Python package. And so this file can even be empty. It's only the existence of the file that makes it a package. So, and this is more important now if you have larger programs, right? So maybe you want to, in this case, I'm developing a solver for partial differential equations. Right? And so to solve these equations, there's loads of different things that we need. We need to define grids where we want to solve them on. Then we need to decide kind of some solvers and preconditioners and I don't know what. And so the way I structured this is that I have an overall package that contains my solver, my software solution. And then so in order to make this a package, I have an init file here. And then now in here, I have a bunch of subdirectories. One is called the numerics. And again, I make this a package. And then part of the numerics, I have a PDE subpackage, right? And again, I make this a package by having the init file. And then finally, in there, I have my first grids.py file. So this is where actually code is contained. And then how do you import that? You just follow down the directory structure. So you say, from mymod, which was the overall directory, .numerics, .pde, .grids, import fdm grids, right? Where fdm grids is a function defined in this grids. And then you can use it. Then you use it just as any other function in your Python program. So you can see with these module package structures, you can essentially break up your code in a much more structured way. And also, when you start using the bigger packages in Python, you will see that it makes extensive use of these packages. The next part is documentation. And so I've already mentioned this, but I just want to repeat it again, because I think it's very important. So whenever you create, especially if you create modules, it's really important that you document what the module does. And the way you do that is in the very first line of your module, you create a string. This can be a single string, or it can be a multi-line string with these triple quotes. And then you describe what the module is all about. So in this case, I have some collection of mathematical functions here. So after that, you can add some code, and then you might define a function. And again, the first line after the function definition is the point where you want to inject documentation. So here again, either a single line string or multi-line string automatically becomes the documentation of that function. And so it's a general guideline on how, so the question becomes, what shall I write in these docstrings? And it's a very good question. It's a very difficult thing, and it's something that you need to learn over time. And so for instance, what's not useful is to write definition of min_sin, which takes a variable x. Right? Then essentially you're just repeating what's contained in the function definition anyway. So what you want to do is you should write, in the first line, you should summarize what the purpose on the function is in a short, concise manner. And then down here, if the function is more complicated and you need to explain more details, then they should go in the second or third line and so on. There's an entire guideline on how to write these docstrings so that you're that people are consistent. And I mean, to be honest, there's multiple guidelines, so typically people are not consistent. But one that is widely used is the Google docstring style. And if you click on this link, you'll find a list on how you should write docstrings if you want to follow this Google style. That's up to you. But for bigger projects, I think that's quite useful. And so what is the advantage of doing all of this? The advantage is that you can access these docstrings later on. And so for instance, if I'm here that depends on the editor, but here in my environment, I can write the function name and then a question mark afterwards, and then I get the documentation down here. Yeah. Next part, testing, that we haven't talked about yet, and that's really, really important. So why should we test? So essentially, imagine you have, we want to test to make sure that our functions are correct, that we haven't introduced any bugs. Secondly, we want to test in order to make sure that once we change our functions, or if someone else changes or proposes changes to our functions, we want to make sure that the fundamental functionality doesn't break. Right? So the idea is that we have a bunch of tests, and people can change our original implementation, but we can always run these tests again to ensure that nothing of the base functionality breaks. And then we can also test in order to make sure that if we if we use our functions in a different environment, that things are still working as expected. So for instance, if you upgrade your Python version, if you upgrade your libraries, if you change to a different operating system, and so on and so forth. And so nowadays there are different development styles. So sometimes people actually prefer to, even before they start implementing something, they first write tests. So they say, I want to develop a function that that calculates the sinus function, right? And then they think about, okay, so what are good tests that should be satisfied if I had such an implementation? Right? And then they come up with 10, 20 tests, and only afterwards they start implementing. And they implement and they tweak the implementation so long until all the tests pass. I mean, this is called a test-first, test-driven development. But typically, one first does the implementation, and afterwards one writes the tests.
The idea is that the test contains the specification.
Well, to some extent, yeah. So which options do we have in Python? There's different ones. There's unit test, there's doc test. Unit test is actually part of the standard Python package. There's doc test, and there's py.test. I will show you py.test because that's the one I'm used to, and I think it's the most powerful one, maybe. So how to use it? So let's assume we have a script or a module. Well, I should say a module actually, where we define a function called absolute value. So the idea is that you put in a float, and it returns the absolute value of that float. And so now we want to write a test for that. So what we do, we create a new file, and that file we call test_script.py. And so typically, whenever we want to test something, we start the file name by test_. So then we automatically know, okay, this file is used to test a module. So then what do we do is we import the function that we want to test from our module. So from script import absolute value. And then we define a function, and again, this function now has to start with test underscore, because py.test will automatically look for functions of that name. We call it test underscore funcs, for instance. I mean, the second part of the function doesn't really matter. And so now we add so-called assert statements. And whenever we have, so it's assert and then a statement which should be true. Right? And this is the tests that py.test will automatically check for. So for instance, we assert that the absolute value of -3 is equal to 3. Right? So that makes sense. Any negative number should become positive. And then if we have absolute value of 5 is equal to 5, any positive number should remain positive. And then it's often really useful to also test the edge cases. So for the absolute value, it would be what happens if you pass in 0. And then in this case, it's just 0. Right? But there might be more complicated test cases. So for instance, you might want to check what happens if you pass in a string in there. What is the error handling? Right, and so now we can run this. And the way you run this is you go to your terminal and you type in py.test. So forget about the exclamation mark. That's only in my environment here. So py.test and then the test script. So test underscore script.py. And the -v flag is just to show some more output, verbose, the verbose flag. You can ignore that. And so then it gets some outputs. That doesn't really matter. It's just it states in which environment it runs. But here's the important part. So here it shows us it runs in the file test underscore script.py. It runs the function testfunc. That's the one that we defined up here. And then the result was that this test failed. So one of the assert statements in here evaluated to false. And we can see which one. It reports in the error statement here. It says assert absolute value -3 equals 3. Right? So that was the very first statement that I had up here. And this was the result. So, so the evaluation of absolute value -3 turned out to be -3. So it then checked assert -3 equals 3. And that, of course, is false. So clearly, something is wrong, right? So we plugged in -3 in our absolute value function, and we got -3, even though we should have gotten 3. So now, what do? We go to our terminal. We are in CO4. We check our script, right? And now we start thinking, okay, so I put in -3, and so if -3 is smaller than 0, that's true. So we went into that statement, and then we returned x, right? And so of course we should have returned -x. If the number is negative, we need to negate it. So then I fix my implementation, and so the same was true here, right? So if it's positive, then I just want to return the value itself. So I fix my implementation, then I go back. Right, so now it's updated, and now I can run my test again. And yes, everything is green. All the assert statements passed, and I'm happy. Okay? And the nice thing is, once you have such a big test, once you have a big test suite, you can be almost certain that if you try it out if you make some code changes or move to a different environment, you just run your test suite. And if everything passes, you're happy that your library still works in that environment. So some guidelines on how to write tests. So essentially, whenever you add a new feature to your module or library, you should add a test for that feature. So when we were working, when I was doing my PhD, we were working on a big ocean simulator. And one of the supervisors always said, if something is not tested in that ocean simulator, it's broken. So automatically, he wanted us to essentially add one test for everything that for any feature that we added to that ocean simulator, to make sure that also in future releases, we make sure that everything still works. So then each test should be should kind of have its own purpose. You shouldn't write 10 tests that essentially do the same thing. Tests should be run relatively quickly, so make sure that it doesn't download gigabytes of data from the web before it runs. So typically 1 to 10 seconds, but well, even 10 seconds is quite large. So maybe 1 second is the maximum. And then whenever you, this is good practice, so whenever you now make changes to your code, you should run the test suite, make sure that everything still works, and only then do you push your changes to the Git repository. And then, of course, the test functions should be descriptive in their names. So don't call them test 1, test 2, test 3, but call them test absolute function, for instance. And so actually often, I mean, you know, sometimes people don't end up documenting their code. And so what do you do then? But if they have a test suite, it's actually worth looking through the tests and looking in, because they're essentially usage examples and how do you use the different parts of the library. So it can even be used as some kind of learning environment. Okay, that was everything I wanted to talk about modules, documentation, and testing. Any questions? Is everything clear? Maybe? Okay, so the next part will be numerical Python. Oops. Oh dear. So now we really dive into the computationally heavy parts of a Python program. And so there it becomes really important. There speed becomes really important. And so we will talk about NumPy, which is a library in Python that allows us to do fast computations in Python. And so for instance, your Mandelbrot simulator that your exercise is all about will heavily benefit from using this numerical Python library instead of just using a standard Python. So yeah, there's loads of literature or loads of documentation about NumPy, so I just skip over that. But if you want to learn more about this, I've added some links here. So NumPy is a module. It's a package, to be precise. It's a package that allows you to do efficient numerical computing in Python. And so why is it more efficient than just using plain Python? Well, the first difference is that it offers very, very efficient array storage and computations. And so technically what's going on is it stores the arrays, or in Python it's just lists, right? And so here we have array, in NumPy we have arrays, and they're stored continuously in the memory of the computer. So rather than having each number stored in potentially different places, here they're forced to be in one piece continuous. And that makes the operations a lot faster. And the second difference is that most of the NumPy functions are actually written in C and Fortran. And that makes the execution much, much faster than a plain Python implementation. And so it was by far not clear that NumPy would become, so by today, NumPy is essentially the standard when it comes to numerical Python. If you go 20 years back or 10 years, you would see that there's loads of different alternatives. But they have more or less lost their importance, so we will focus on NumPy. So I want to show you a first example, a minimal example that maybe demonstrates the main things that we will talk about. So there's a lot of code here, but I just want to show you the result. So the result is a figure where we have some data points. So these, well, essentially we have some data points here, these blue dots. And they were created by drawing points from this red line here and adding some noise. So essentially, take a point on the red line, add some noise, and then we ended up at that first data point. And the same thing with all these different data points. And then what this program above does, it tries to fit, so it takes only the data point, so it forgets, it doesn't know about the red line, and it tries to fit a line through all these these data points out there. And if it fits the line in a best manner, then you get this blue line here. And you can see, at least for this example, right, the blue line and the red line, they coincide quite well. So we were able to reconstruct essentially the original line more or less from the data points. So how do you do that in NumPy? So we go through this now step by step. But I just want to give you a big overview of the program. So of course, in the first part, we import the relevant libraries. Then we will have a section of the code where we create the data points. So these are both the red line and also the blue lines. It's this section. Then the next section, we will solve a least square system. So that's essentially the part where we will find the blue line that matches as best as possible the data points. And then at the end, we will plot our results. So you can see it's maybe 20 lines of code, and it does a fairly complex set of operations. But let's go through this line by line. So the first step is to import the NumPy package. And the way we've learned about this just before, we can write from NumPy as NP. And so this here I just rename. In future, I want to just be able to write NP dot function name instead of having to write NumPy all the time. I'm just being lazy here. Okay, so then the next thing that we want to do is we want to create a bunch of data points. These blue data points that we've seen before in the plot. And the way you do that is we first n defines the number of data points that we would like to have. And then essentially what I want to store is I want to store the x values of these data points and the y values. Okay. And the way I choose the x coordinates is just by a linearly spaced data points between 0 and 1 and a total number of n in data points. So there's this function n.linspace that does exactly that. So the result of that command here is that you get a so-called NumPy array, which is just a bunch of, in this case, numbers, and it contains all the 20 x coordinates of our data points, linearly spaced. So then we need the associated y data points. And the way you do that is you use this, we now need to apply our function to every data point that we have. And in NumPy, you can just write -2 times x plus 3. So in normal Python, right, we would have to loop over all the x coordinates and then apply this function on each x coordinate and put it in a new list. But in NumPy, we can do so-called array operations. So we can just write -2 star x plus 3, and it will return a new array where element-wise this mathematical operation has been performed. I'll go into that in more detail later on. But essentially here we apply the function to all of our x coordinates, and then next line we add some random noise to each data point. And so the result is, again, another NumPy array with 20 entries and containing the function value for each of the x coordinates. So then we need to solve this. So now we have our data points. Now we want to reconstruct what the line is, the line that fits through this data points. And the way you do that is you solve one way of doing it is that you solve a so-called least squares problem. And conveniently, we have a module in NumPy that does this for us. It's in the NumPy package and inside the linalg package, and the function name is least squares. And so, well, I won't explain exactly why you have to do exactly this now, but essentially you can look up the documentation, and it turns out that you need to provide these x values, and then you also need to, of course, provide the values of your data points. And then what you get out is you get a result, and the result contains essentially two important numbers. The first one is the steepness of your line, and the second one is the offset of your line. So that defines what our reconstructed line of these data points looks like. Right, so after these lines, we have A containing the steepness or the gradient of the line, and then B contains the offset at the point x equals 0. So then our approximated line now is A times x plus B equals y. That was the blue line in the graph. And so finally, we want to plot all our results. And the way you do that is we use another package. It's called the matplotlib package, which is often used in combination with NumPy. And so what we do is we import from matplotlib called a package pyplot, and then import this as plt, or the module pyplot, import this as name plt. Right, and then we essentially create one plot for each of these, for the red line, the blue line, and the blue dots. So we have plt.plot x and y. These are our data points. Then we have x and ax plus b. This was the fitted line with the coefficients a and b. And then x and y line, was the original line that we had. And then we have some legend, and then we show the graph. And this is the result that we had. But I will go a lot more details in all of this in the next.
I don't really get how, when you do plot, and two of them becomes line, and the other is just dots.
Right.
So
again, so I will explain this later, but it's essentially the third argument. Yeah. So if you, the O, yeah. if the string here is an O, it becomes dots. Yeah. And if you use B, it becomes a line that is blue. And if you use R, it becomes a line that is red. Okay. Yeah. But I mean, I will show you in a second later how you can customize your plots to your needs. All right, so that was a kind of a quick demo. Now let's go all the way to the basics. And I want to show you some of because it's important to understand the fundamentals of NumPy in order to understand what's going on. So the most fundamental data structure, or the most important data structure that NumPy provides you is an array. And essentially, they're just a list of items that has to be of the same types. And the way you construct that is you write np array, and here you can provide a Python list, and the result will be that Python list converted into a NumPy array. So for instance, the first one contains three numbers, three floating point numbers, because we have a list of floating point numbers. The second example will be an array consisting of strings. So some important properties of NumPy arrays that makes them different to Python lists. So first, arrays have a fixed size. So these ones here have size 3, and we cannot change their size. They will always be of length 3. The second one is that they have one associated data type, and all the objects in that array has to be of that data type. So you remember in lists, you can have a float and then a string and so on. That's not valid in NumPy arrays. They always have to be the same. But arrays are mutable objects. So after creating this array, you can actually change one of the values inside the array. So you can set the first component to 0, for instance. So I've already shown you how you can convert Python lists into arrays, but often it's useful there's some convenience functions for arrays that are often used. For instance, if you just want to create an array that contains zeros, you can write np.zeros and then the number of items that you want to have. Right? Then you get 3 items, 3 zeros here. The same thing works with ones. You can write np.ones 3. Right? And once you have ones, you can essentially get any number by just writing 100 times. And then you can even use np.empty if you know that the values don't really matter that are inside the array. Right? Maybe you straight after that line, you start looping over every entry and set it yourself anyway. And so then you can use this np.empty, and it's slightly faster than np.zeros and np.ones, because the machine doesn't have to zero out the memory or set the memory. So if you're if you're concerned about speed, you can use this. So one thing that is very often used or very useful is if you want to have an array containing a sequence of numbers starting at a starting point, going all the way up to an endpoint, and you want to have a linear spacing between, or constant spacing between each number. And that's exactly what this linspace function does. So you provided an endpoint and a starting point and an endpoint and a number of the array length, essentially, and then you get an array out. And you can, there's this, right, so that's how it's shown here, right? So you have linspace 0 to 0 all the way to 10 using 8 data points, right? So you get the first one starts at 0, the last one starts at end, and in total you have 8. And sometimes it's actually useful to exclude the endpoint, and then you can use this argument endpoint equals false. And so then it still starts at 0 and it goes all the way to, well, to 10, except that 10 is not included. Yeah, exactly what I've said. So use endpoint to exclude the last data point. Then we have arange. So range is the equivalent of range in Python. So remember, range in Python gave you a list starting from, well, it was an iterator, but more or less a list starting from 0 all the way to a number that you provided, or starting it, and with integer increments. And so the same thing in NumPy is called arange. It's a bit more powerful, so you can say, you can provide the starting point, the end point, and the step size that you want to have from each point to the next. So in this case,
you have endpoint equals false here also, or can you either include
well, yeah.
the last point?
To be honest, I don't know. Okay. The question is, can you have endpoint equals true or false here? You might be able to. We can check. So how do we check? We do np.arange question mark. And so here we get the arguments, right? So the arguments are start, stop, and step, and then potentially dtype. So there's no arange. Right, let's have a break and let's start again at 1:15.